Everyone, so today we are going to discuss the Fraunhofer single slit diffraction. So in this topic we will see how light when passes through or rather touches a sharp object and falls on a screen bends. So in this illustration we can see that this is a source, and when the light ray that we consider as travels in a straight path, so this should be the path of the light ray, and similarly here this should be the path of the light ray. So this should be the geometrical shadow, and after this part this is the objection. So after this part the illumination should be there, and also after this part the illumination should be there. But when we observe in our real life, we can see that this is the only actual shadow part, and here illumination is there, and also here illumination is there. So the assumption that we made that light travel in a straight path and there shall be a geometrical shadow in this area, it is not true. In the geometrical shadow there is actual illumination. So this is the case when the object is like this position, objection rather, and this is the case where the objection is kept like an opening. So we consider that this is the geometrical illumination, but in real life when we observe we get that this is the actual illumination. So here also light bends like this, and if we see it in a simulator, then we can see that if we take a slit, like these edges are very sharp, then a fringe pattern, this one, is observed on the screen. So from this source we are taking the light ray, or rather light beam, and passing it through a small slit. So this one is this, and this is the screen. Then we can observe that there are these patterns we can observe. Those are shown in this screen. So there we get a central maximum and a corresponding or next minimum and maximum alternatively. We can see that by the illustration the central maximum is very bright, and alternatively the brightness decreases, or rather intensity decreases. So we will get into the mathematical aspect of this topic. So we will start with a electromagnetic wave. So as we know that light is an electromagnetic wave, so it can be written as, let us write a general electromagnetic wave. How we write it? As, let us take it as E as a wave, and then we get a maximum amplitude, and then cos of kx minus omega t. So now our setup that we will see in our Fraunhofer single slit diffraction will be like this. We will take a slit of width b. Let us just draw this a little bit bigger. So this will be the slit, and the slit width we are gonna take is b. So this is the screen, and this is, let us take d, the distance between the slit and the screen, and note that d is very greater than the slit width. D, and this is the screen, and let us take that if this is this is the middle part of the slit, then this is a line passing through this middle part. So, or let us take it as any point. So to avoid our confusion, so let us draw it a little bit above. So this is passing through this point, and let us take this as S axis. So here it will be S equal to 0, here it will be S equal to B, as we have taken that this slit width is B, and a light ray is traveling like this from this point, and from this arbitrary point it is like this, and this point we'll consider it as P. So we will see that what is the effect of the light wave at P. So this is P and this is D, and as this is very much bigger, therefore we will assume that the light ray are traveling in a parallel path to each other. And if we see the condition for Fraunhofer diffraction, we take that the source and the screen both are placed at infinite distance from the slit. Therefore, if our angle, this one, is considered as theta, therefore this is also taken as theta, and we will drop a perpendicular over here. So let us suppose that this light wave travels a distance of x, then it will travel a distance of x plus delta x, where delta x is this part, delta x, and how much it will be. So this will be theta. It is very small, so it's very hard to draw, but we'll try. So we are showing this part over here in a bigger version. So like this, something is there, or rather a triangle is there, a right angle triangle. So this is the thing, and if this is theta from horizon, then this will be theta from vertical, and this is, let us take any position S over here. And then, so if it is S, so this is the delta x, so we can see this delta x equal to S sine theta. So this is something like this, and if we consider a ds element, so this now this single slit is divided into infinitely small elements of slit. So we will take one of those as ds. So from one of those, electromagnetic wave will come. So let us assume that this is dE. So this is the dE, and let us rather take it as dE1. So dE1 will be something like amplitude. Let us take A1, and then we will write cos of k into, in place of x, it will be x plus delta x minus omega t. So similarly, we'll get dE2, A2, and then cos of k into x plus delta x. This will not change, and because we have assumed, we have taken our mathematics like that way, that delta x is always, if we see for whole slit, then it will be S sine theta. Therefore we will get n number of DEN equal to AN cos of k into x minus x plus delta x minus omega t. We will get this, and one thing we need to remember, that amplitude over here, that is A or A1, A2, AN. So this amplitude directly proportional to ds. So think it like a camera aperture. So how much the aperture radius will be bigger, the intensity of the light entering the aperture will be more. Therefore this amplitude will be directly proportional to s, and let us consider this as amplitude equal to a constant c and then ds. So for any arbitrary element we will get dE equal to c ds, that is the amplitude, and then cos of k into x plus, so delta x is our s sine theta. So we'll get s sine theta and then minus omega t, and we will add all this elemental electric field from this s equal to 0 to s equal to b. Therefore energy, or sorry, not energy, the electric field that we will get at point P will be integration of 0 to b c cos kx minus omega t plus ks sine theta ds. So if we integrate, and remember that this p is a function of x, because if we see here, let us take this as d we have taken and this as p, therefore tan theta is equal to p by d. Therefore as the angle is very small, therefore theta will be equal to p by d. Therefore we get a direct relation between p and theta. So therefore we can write here E of p or E of theta, which is varying with respect to independent variable, that is p and theta, both are same. So it will be c whole upon k sine theta into sine of kx minus omega t plus ks sine theta from s equal to 0 to s equal to b. So now E of p will become c by k sine theta into sine of kx minus omega t plus kb sine theta minus of sine kx minus omega t. So we get this. Now we'll apply the formula for sine of c minus d. So it will be 2, or let us write it as k sine theta, then 2 sine of c minus d by 2, that is we will get kb sine theta by 2 into cos c plus d by 2, that is we will get kx minus omega t plus kb sine theta by 2. We are getting this one. So if we rearrange and write it, then we will get 2c by k sine theta into sine of kb whole upon 2 and then sine theta, and then here we get, so this is a separate part, and cos of kx minus omega t plus kb sine theta by 2. So if we compare it with our electromagnetic wave equation, this one, so we can see that this cos part is there over here we can see, and the E naught with that is our amplitude. So this is our amplitude. So this part is our amp, and we know that intensity. So we are calculating it for point P. So let us write I of P is directly proportional to amplitude, amp, and then its square. So I of P will become, so we'll remove this proportionality with a proportionality constant and let us take it as 2. So 2 will become 4 and then C square, and then we will take a new constant C1 whole upon. So let us just divide and multiply it with B by 2 to make this term in the denominator here itself. B by 2 whole square, and then KB sine theta by 2 whole square, and then sine square KB sine theta by 2. Now we will take KB sine theta whole upon 2 equal to beta, which is equal to K is equal to 2 pi by lambda, and this is 2 is there, and then B sine theta. Therefore we get beta as equal to pi B sine theta by lambda. So from here we get I of P equal to, so this numerator part we will take it as I naught, as all these things are constant, and then we will take sine square beta whole upon beta square. So this is the intensity due to all the interference of this small elemental wave over here at P point. So now what this equation tell us? So this is intensity at P. So now this equation tell us about the maximum and minimum of our intensity. So first we will see about the central maximum. So at central maximum we can see that theta is 0, therefore we will get central maximum over here. So if theta is 0, then over here if we put theta equal to 0, then beta is becoming 0, but we cannot substitute directly beta equal to 0 over here, then it will become an indeterminate form. So rather we will use limit. So first case, that is central maxima. So central maxima we will use limit beta tending to 0 I naught sine beta by beta whole square. So this is equal to I naught because limit x tending to 0 sine x by x equal to 1 we know. So our intensity at 0, that is the central maxima, will be I naught, and we will see the minima. Now this is our intensity, and our intensity minima. So I of P equal to I naught sine square beta whole upon beta square. Now if we see that to get our intensity minima, we need this sine beta equal to 0. So what will be our condition? That sine beta should be equal to 0 and simultaneously beta should not be equal to 0. So now if sine beta is equal to 0, then beta is equal to n pi because at n pi sine becomes 0. And watch carefully that here n cannot be equal to 0, because if n is 0 then beta is equal to 0, but we have to match both the condition, so beta cannot be 0. Therefore our n is 1, 2, 3, or rather let us take it as minus or plus minus n pi. So in both the sides we will get the minimas. Therefore our beta is pi b sine theta by lambda. So pi b, pi by lambda b sine theta equal to n pi plus or minus. So our b sine theta becomes n lambda plus or minus. So this means that we will get the minima like this. Over here, you cannot see it. I'll just change the color of the pen. So over here. So alternatively, we will get minima. And we will see for the maxima. So for the maxima, what we will do is, we will maximize the function. For maxima. So for maxima, I of p equal to I naught sine square beta whole upon beta square. So if we do it, d I of p, so here we can also write this as beta, because we can see that beta depends on theta and theta depends on p. So theta depends on beta depends on p. We can write both. So this will be equal to I naught or let us say d by d beta. So it is I naught into, here it becomes beta to the power 4 into 2 sine beta cos beta into beta square minus of 2 beta sine square beta. So to maximize this one, this should be equal to 0. Therefore we get the condition, that is 2 sine square, just a second, this will be cos beta, and then yes, beta square, and then yes. So this is cos square beta, and then let us take it 2 beta square equal to 2 beta sine square beta. So it is coming, just a second, here I think yes, square will not be there, and let us take it as minus, so it is equal to 0. Therefore if we take beta into sine beta common, then we get beta cos beta minus sine beta equal to 0. Therefore either beta can be equal to 0 or sine beta can be equal to 0 or beta can be equal to tan beta. So now this case is not possible because of this. If beta becomes 0, then it will be, intensity will be tending to infinity and it will be an indeterminate form. So sine beta cannot be equal to 0 because we have taken it in this condition, sine beta is equal to 0. So this is the condition for minima. Therefore compulsorily tan beta should be equal to beta. Now if we plot the graph of, let us take y equal to beta and y equal to tan beta, therefore the graph shall come like this. So this is the y-axis and this is beta. So tan curve will be something like this, and then here it will be pi by 2. I am just drawing a rough graph over here. So it will be going like this, and again it will be minus pi by 2. So it will be just like this. So if we plot this graph, so this is y equal to tan beta. So this is y equal to tan beta and y equal to beta. The graph will be a straight line passing through the origin. So this will be the graph. So all the intersection point will be the solution of our this equation. So what are the intersection point? So we can calculate it by drawing graph. So I have done it, so I will write it. So beta will be approximately equal to plus or minus 1.43 pi and then plus 2.46 pi and so on. So if we put beta equal to 1.43 pi in our intensity equation, then intensity of 1.43 pi becomes I naught by 22.2, that is 4.5% of I naught. Therefore the graph is coming something like this. We will draw the graph of the intensity with the position now. So let us draw the graph carefully. So let us take this, and for our convenience we will take the dots. So this is the one, and then this will be the intensity one. So at the central maxima we will get maximum, and then it will just go like this, and it will come and go like this, and it will go on decreasing. So it will touch a maxima over here and then a minima and then like this. So this will be our I naught, and this is the graph of intensity at any point beta, and this is beta. So our graph will be like this. So this will be 4.5% of I naught. That is our first minima or maxima, sorry, and our minima will be all zeros. Hence we get our diffraction pattern like this. We can see that here is the central maximum, and after the maximum we get a minimum over here between two maximas, and then the intensity of the consecutive maxima decreases and eventually it becomes 0. So this is the whole Fraunhofer single slit diffraction. Now the key points that we need to remember is the diffraction is a spreading of wave as they pass through an opening. So we'll write key points over here. Key points. So first point, diffraction is the spreading of wave as they pass through an opening. And why it is formed? Because the pattern is caused or formed by interference from all elementary part of slits. And we will write the driving principle. That is Huygens principle. HUY Huygens principle. And the fourth one is the intensity formula, that is I of theta is equal to I of beta is equal to I of P is equal to I naught and then sine square beta by beta square. And we'll write beta equal to pi b sine theta by lambda, and b is the slit width, and we have taken that theta is this angle at any arbitrary point P on the screen. We get the theta from the horizon. And then sixth point would be, so 1 2 3 4 5 6, sixth point would be the minimum or the dark fringes. Dark fringe, that is, it occurs when b sine theta equal to n lambda and n equal to 1 2 3 and so on. We can also take minus, nothing will happen. And the seventh point, that the central maximum is twice as wide as the other maxima and is far more intense. That is 2 times, or let us say twice as wide, that is from minus lambda by b to plus lambda by b as the other maxima. And is far more intense. So if we give a summary of today's lecture, so today we started with a simple observation that light passes through the narrow slit here in the simulation that we saw. which creates a complex pattern, this pattern that we are talking about. And we used the Huygens principle to this model, treating the slit as infinite number of wave sources. That is, we have taken the elementary sources over here, ds, at different point at arbitrary distance s from any of the end of the slit, and then we integrated it. So by using calculus to integrate all of their contribution, we derive the complete intensity formula as I of p. This is I naught sine square beta by beta square. So this single equation perfectly explain our observation, the bright wide central maxima, and also the exact angular location of the dark minimum, and the rapidly decreasing brightness of the secondary maximum. And it's a complex wave that we see over here, which causes diffraction. So, and at the last we gave the summary or key points that we need to remember from this lecture over here. So this is it for today. I hope everyone understood, and thank you for watching.